All right. We are, I'm going to erase this out of here. We are now at data that curves like quadratic, but it doesn't end up like a quadratic, where the quadratic will curve back up more extremely. Our data now, and actually I should put it over here so it's across this little line. So as we have trials that get larger and larger and larger, it looks like our data right now is doing this. But what it's not doing is coming back up again, or double humping and dropping back down again. Remember how Usain had that cool little point where it changed a little bit? It was humping up and then it started humping back. None of that. You don't get, those are called inflection points. I'm not sure if I mentioned that in your project or your exam or not. Not important. You don't get that. You get this constant curve. But what's interesting about it is the further you go out, the closer the data keeps getting to this horizontal axis. Will it ever touch 0? No. It can't mathematically, can it? Because if you keep dividing a number by 2, you're never actually going to get to 0. You just keep getting half smaller. There's an interesting paradox, speaking of riddling over here. There's an interesting, called Zeno's paradox, I believe. No, I could be wrong about that. I could be calling it the wrong thing. I can prove this marker will never hit the ground if I drop it. I can prove it to you mathematically. You ready? Well, how high do you think it is above the ground right now? 6.5 feet. Let's go back to 6 feet, make it easy. Math easy. Because in order for it to hit the ground, it first has to fall halfway. That takes a certain amount of time, right? Very quick. And then in order for it to get from 3 to the ground, it then has to fall halfway again. Right? And then you get from 1.5 to the ground, it has to fall halfway again, which is big. You guess like, where you're going with this. And then to get from there to the ground, and each of these things takes time, yes? Now, granted, it's not a whole lot of time, but to get from here to the ground, it has to fall half that way, and then half that way. It's never going to get there, because those halves never become 0. So what's the paradox? When you actually drop the marker, it hits the damn ground. So how do you explain that if the mathematics doesn't agree with what actually happens? That's why it's called a paradox. And the answer lies in something called a limit, and don't worry about that. It's kind of, you guys actually did it, believe it or not, when you were doing my instantaneous rate of change on my bike. I just didn't tell you were doing it because I didn't want you to be pissed off. But the idea, and Amber, goes back to your rounding, is these will never touch, but eventually they get close enough to arguably say they're touching. For the same reason, remember the aspirin you took in 1993 for the headache? There's still a little bit of that in you. Because aspirin has what's called, don't feel bad about that. Aspirin has what's called a half-life, which means after a certain period of time, half of whatever the drug is in your body is gone. Okay, I don't know what aspirin is. Aspirin is something like 8 hours, I think. So say you take 500 milligrams of aspirin. 8 hours later, how much is in your body? 250. 8 hours after that, how many? 125. 8 hours after that? 60-ish. 8 hours after that? 30. 8 hours after that? 15. Now we're like 2 days later or 3 days later, right? Then 8 hours after that? 4, 2, 1, a half, a quarter, an eighth, a 16th, a 32nd. What never happens?
It never reaches 0.
You never zero out. But there comes a point where it doesn't matter because there's such a tiny amount of it in your body that it's essentially 0 anyway. That's where your practical versus mathematical comes in. Go ahead, sister.
Called where it never actually reaches it, but it just goes like a
It's a great little word from Greek. They took 3 things. They took 3 prefixes and put them together. The word that you're looking for is called an asymptote. And I forget the actual Greek. The asymptote, I think it means like doesn't fall in line, or falls in line with, or something like that. The idea is this axis is asymptotic with the data, in that the data comes down to it and wants to get down to it, but it can't actually get to it. It can only get infinitely close. So then the question is, how close is close enough? Don't worry about the answer to that right now. We'll deal with that kind of stuff like in your quizzes and things like that. I promise. I promise. But that's what the technical term is. Do quadratics have these? Do quadratics have... Quadratics curve like that, yes? Sure. Careful, they don't. This is what's so weird about quadratics. When you draw a parabola in your mind, you tend to draw it like a U shape, yes? meaning it goes vertical. They never go vertical. They can't go vertical. Explain to me why a quadratic can't go vertical.
Because your y value would have to be 0.
Oh my goodness. Suppose I'm on my bike and you're clocking me. And you've got that quadratic data like before. Suppose my curve went vertical. And let's just suppose, just for grins, that my curve went vertical at 8 seconds. So, I have this quadratic model, and it goes absolutely vertical at 8 seconds. Where was I at 8 seconds? I could have been there. I could have been, maybe, or maybe I'm just right there. See, the problem is, if it goes vertical, you no longer have one x, one y.
I meant it was going to an asymptote.
Oh!
I meant the
Well,
asymptote.
it doesn't, but it doesn't. It does an asymptote. Because, now, good, Tom, what Tom is saying now is, it keeps getting steeper and steeper and steeper. That is a correct statement. But it never asymptotes out, because if it asymptotes out, that means there's going to be a line beyond which it can't push. Thank you for that. Let's suppose, I love this, by the way, thank you. Let's make sure we understand what Tom is getting at here. Make sure the camera's pointing at this board now. Why quadratics can't have asymptotes. Awesome discussion. So here's a quadratic. Let's suppose it does. So here's a graph of y equals x squared, just to make life easy. Y equals x squared. And let's suppose it does have an asymptote somewhere out here that it can't get to. Give me an x value that it can't get to, friends. Give me an x value that it can't get to. Let me get on this side. How about 10,000? I mean, 10, clearly 10 can be found on that curve, right? So let's make it 10,000. It can't get out to here. 10,000. Can't get there. Can't get there, right? Problem is, it can. When x is 10,000 in that curve, what is y?
10,000 squared.
10,000 squared. 10 million. Exactly. I think I did that right. 10 million. No, 100 million. 100 million. 8 zeros. So quadratics can't have vertical asymptotes by definition of the fact that whatever the number you want it to not get to, it will go, and it will get to it. I mean, essentially, that's what's going to happen. It's going to say, oh, you want to have a vertical asymptote? Screw you, plug it in, and what pops out is not your asymptote, it's the value it gets to. Now, you could argue that maybe it's got a horizontal. Well, it doesn't get below 0. That's not an asymptote. An asymptote isn't one that it comes down to and pops away from. It's one that it comes down to and tries to get closer to, infinitely close. Thank you for that. That was wonderful. And that's how, Amber, your rounding kicks in over here with the exponential model. That's what's going on over here. So let's pop this guy back. Those are phenomenal questions, guys. Thank you.